This is Lesson 21 in our Calculus 3 series, Double Integrals over Rectangles. As we start our lesson on double integrals over rectangles, let's think back to Calc 1 about the development of definite integrals there. We said that the integral from a to b of f of x dx is equal to the limit as the maximum of delta xi goes to 0 of the summation I from 1 to n f of xi star delta xi. Remember that this is a Riemann sum where xi minus 1 comma xi is a partition of the interval ab. The evaluation point xi star is a point in that ith interval, and delta xi is the width of that ith interval. Now for most of the problems we do in class, we have a constant delta x. We usually take delta x to be b minus a over n, and that simplifies the situation quite a bit. But we could partition the interval ab in any way we want, and in which case we just want to make sure that the maximum length of a subinterval is going to 0 as we take this limit. And for a function f of x with values greater than or equal to 0, graphically what this gives us is the area under the graph of f of x over the interval ab. So here's that area, and remember that the summation we're taking here is the sum of areas of rectangles defined by the partition and by the function's evaluation at that xi star point in each interval. For example, we could have a partition that looks like this. A is always x0 and b is always xn, but we could have, say, x1, x2. Remember that the delta xi don't have to be the same, so we could have different widths for these subintervals, and that's okay. Here's xi minus 1 and xi, so this is the ith subinterval. Here's xn minus 1, and as we said, b is xn. And xi star is a point in the ith interval, so in each interval we're choosing a point at which to evaluate f and use for the height of the approximation rectangle. So for example, we can use the midpoint rule that says on each interval, evaluate f at the midpoint of that interval. That tells us in our first interval, we're going to evaluate f here, and we're going to have that height for our approximation rectangle. In our second subinterval, we'll have a similar height there. In our ith subinterval, here's our midpoint, here's the function evaluation at that midpoint. In our last interval, for example, here's the midpoint, the function evaluation at that midpoint. And we'd fill up this area with these kinds of rectangles, and that gives us the value we're looking for that area. And recall that we compute this definite integral not by taking a limit, but by using the fundamental theorem of calculus, where we take the antiderivative, evaluate at the endpoints, and subtract. Now consider the situation where we have f of xy greater than or equal to 0, and we're looking at the volume under the surface over the rectangular region given by a less or equal to x less or equal to b, and c less or equal to y less or equal to d. So here's our surface, and here's our domain. And the volume that we're looking for is the volume of this solid here. So we want to make a similar approximation. Instead of using rectangles, now we're going to use rectangular boxes and take the limit as the length and width of those boxes goes to 0. So we start by partitioning the intervals AB and CD. And so that'll look like this on our domain. On each of these rectangles in the domain, we have to choose a point at which to evaluate the function and use that height as the height of our box. And so on the rectangle in our domain defined by xi minus 1 to xi and yj minus 1 to yj, we need to choose a point, and we call that point xij star, comma yij star. And we find the corresponding function value, which is the height of the surface, and that's going to give us the height of our rectangular box. And so our rectangular box over the ij subrectangle looks like this. And we would do this for each of these rectangles in the domain. So for a function with positive z values, the volume under the surface over the rectangle R, defined by a less or equal to x less or equal to b, and c less or equal to y less or equal to d, is the double integral over R of f of xy dA, this is a measure of area, is equal to the limit as the max of the delta xi's and delta yj's go to 0. So this is saying the distance between the x's and the distance between the y's are going to 0. We're taking the sum over I and j of the volume of that rectangular box. And so that's given by the height multiplied by length and width. So delta Aij is delta xi times delta yj. That's just the area of that small rectangle. Again, the xi and the yj are partitioning the intervals on x and y. And the star point is the one that's chosen at which to evaluate f and get the height of our box. So let's take a look at an example. Estimate the volume of the solid enclosed by x equals 0, x equals 4, y equals 1, y equals 3, the xy plane, and z equals 4 plus 2x plus xy with a Riemann sum using 8 pieces. So they're telling us to do the Riemann sum with 8 pieces. Let's take a look at our domain. We've got x going from 0 to 4, and we've got y going from 1 to 3. Now they're telling us to do the Riemann sum using 8 pieces, so the most natural way to divide this region into 8 pieces would be to have both delta x and delta y constant at 1 unit each. So now we have our 8 subrectangles. But notice that it's not telling us where we should be evaluating the function to get the height. Remember that in the formula for our Riemann sums here, we have this point xij star, yij star. That is the point in that subrectangle at which we are evaluating the function and using that function evaluation as the height of our rectangular box. So notice that this kind of question is a little bit vague unless they specify what rule we should be using. For example, we could use a midpoint rule similar to what we had in Calc 1. For the midpoint rule, we would want to evaluate f at the midpoint of each of those rectangles, which means we're going to take the midpoint of each of these x intervals and match that up with the midpoint of each of the y intervals. So that's going to give us the point 1/2, 3/2 here, and 3/2, 3/2 here. And so our volume will be approximated by the height times length times width. Keep in mind that delta x and delta y are both 1 here, so this is just 1. So we've got the area of the base times the height of the box. And we're going to do that for each of these subrectangles. So take a minute and make those evaluations and check to see that you agree with the values I have here. And our approximation is then 96 using the midpoint rule. But we didn't have to use the midpoint rule because in this problem they didn't specify a rule. So we could have chosen, for instance, a lower left corner rule where, again, we would have 8 pieces to our Riemann sum. And the lower left corner rule means that for each of these subrectangles we're going to evaluate at the lower left corner of the interval. So for example, we're at the point 0, 1 here, 1, 1 here, 2, 1, 3, 1, 0, 2, 1, 2, 2, 2, and 3, 2. And that approximation gives us 74. Again, take a minute and see that you agree with those values. Now, to have just a more general idea of what kind of range this volume should be in, we could just take an overall overestimate and an overall underestimate using one large box. We could take the highest point on this surface over this region and take one box of that height. We could also take the lowest height of the surface over this region, and take one box of that height. And those would give us an overall overestimate and an underestimate for the volume that we're looking for. So if we do that, we need to know the absolute max and min of this surface over this region. So we take a look at our first partials, set them equal to 0 so we can find any critical points within the rectangle. But here we notice that the only critical point we find is not in our rectangle. So that says the absolute extrema we have for this surface over this rectangle are going to be along the boundaries. So we need to check values for f along the boundaries. For example, when x is 0, we have y ranging from 1 to 3. When x is 0, though, our function reduces to the constant function of 4. So at any of these points, we've got a function value of 4. When x is equal to 4 and y ranges from 1 to 3, x is equal to 4, so our function reduces to 12 plus 4y. And with this function, we're going to have a minimum when y is equal to 1. That function value would be 16. And we're going to have a maximum when y is equal to 3, and that would be a value of 24. When y is equal to 1 and x is ranging from 0 to 4, when y is equal to 1, our function reduces to 4 plus 3x. And with an x value of 0, we're going to get a minimum there, a function value of 4. And with an x value of 4, we're going to get a maximum here, a function value of 16. And when y is equal to 3, our function reduces to 4 plus 5x. We get a minimum when x is equal to 0, function value of 4, and we get a maximum when x is equal to 4, a function value of 24. So we're really just looking for the highest and lowest values on this surface so we can get an overestimate and an underestimate for the volume that we're looking for. We notice that the lowest value we achieve here is 4 and the highest is 24. So our overestimate for the volume will use the maximum function value as the height. Now this is our change in x is 4 units, change in y is 2 units, our height's 24, and we get 192. That's the volume of that box. And using a minimum function value of 4, we get again the change in x, the change in y, now this height, and that gives us 32 as an underestimate for the volume. So that tells us the actual volume, and hence our approximation to volume, should be between these two numbers. And remember, we got 96, so that seems valid so far. Now, when I defined the double integral above here, I said that f of xy was greater than or equal to 0. And I really only said that because I wanted to talk about the volume under the surface. But we can define a double integral like this for function values that are greater than, less than, 0, equal to 0, doesn't matter. And keep in mind then that when the surface is under the xy plane, our volumes will have a negative sign, similar to what happens with integration when our function values are negative. Right? The areas under the x-axis come up with a negative sign. Same thing here, the volumes under the xy plane are going to show up with a negative sign. And that's because the function evaluations over those subrectangles are negative. So essentially that height is negative. Now how can we compute a double integral without using limits? We're going to look at iterated integrals. So consider a of x to be the integral from c to d f of xy dy. Now let's take a look at what's happening here. This dy is telling us that y is changing. Y is the variable. So that means x is fixed here. So what this represents is the area of the slice for a fixed x. So here's our surface f of xy. We're fixing x, whatever that x value is, and we're looking at this integral dy as y changes from c to d. So we're saying as y goes from c to d, let's add up all those function values. And that gives us this area, the area of this slice. Now, if we took all of these areas and added them together, we would get the volume. So we want to take all of these areas and integrate over x going from a to b. So let's integrate these areas over x. What that looks like is this iterated integral here. First we integrate on y ranges from c to d, and then once we make that computation, we integrate that result on x, and x goes from a to b. That's the iterated integral. Now the way I've described it here, it seems like that gives us also the volume that we're looking for. And in fact it does. And Fubini's theorem tells us if f is continuous on the rectangle, where x goes from a to b, y goes from c to d, then the double integral is equal to the iterated integral in both directions. So we could integrate on y first. Notice dy and c and d are on the inside, and then on x. Or we could integrate with respect to x. Here's the dx and the a and the b, those are on the inside. Integrate with respect to x, and then with respect to y. So this is how we're going to make our computations for our double integrals. But I need to point out something very important. This idea of switching the order of integration and just switching the bounds is only this easy when you're over a rectangle. You're going to see in the next lesson that it requires a bit more work to switch the order of integration. So it's only this easy when you're over a rectangle, which means that all of these bounds are constant. Okay, so keep that in mind. Let's take a look at the same example we had above. Now let's calculate the actual volume. So here's our surface. Here are our bounds for x and y. So we could set up either of these iterated integrals. This one does dy first. The y bounds are on the inside with the dy. And after that, we would integrate with respect to x going from 0 to 4. Or we could integrate with respect to x first, and then once we're finished with that computation, integrate that result with respect to y. Either way, we'll get the same solution. So let's do it both ways. So we'll start with integration on y. Now what this is saying is that y is the variable and x is constant. It's just like taking partial derivatives, but now we're doing integration. But it works the same way. This dy is saying y is the variable, so x is held constant. So when we look at this, let's integrate. That's going to give us a 4y plus 2xy plus xy squared over 2. And now we have to plug the bounds in of 1 and 3. And this is really important. I want to point out here, don't be confused by these bounds. Where are these bounds getting plugged into? This came from the integral on y. This is saying y equals 1. This is saying y equals 3. The 1 and the 3 get plugged in for y. So we have a 3 here and a 1 here as we make our computation. And once we finish all of that simplifying, then we're going to integrate that result with respect to x and use the proper bounds for x. So take a minute and look over my computations here. Make sure you agree. And so integrating with respect to x, we get 8x plus 8x squared over 2, or 8x plus 4x squared. And we've got our bounds of 0 and 4. And now these are bounds on x, so we plug them in here, and we get 96. Now this is the actual value, and it was also the value that we got from our midpoint rule. Let's go on to find the integral in the other direction. In other words, integrating with respect to x first and then with respect to y. Here we're saying that x is the variable and y is constant. So let's integrate this with respect to x. That's going to be a 4x plus 2x squared over 2 plus x squared over 2 times y. And that gives us this. And similar to what we had before, let's just point out that this is x equals 0 and this is x equals 4 because we just integrated on x. So that's where we're going to plug these values in. right? So x is equal to 4 here, and x is equal to 0 here. Simplifying, we get 32 plus 8y, and we want to now integrate this with respect to y and its bounds. So 32y plus 8y squared over 2, or 32y plus 4y squared. Y is going from 1 to 3, and we get the same answer of 96. Let's take a look at another example. We want to evaluate the double integral of y e to the xy over rectangle R, where x goes from 0 to 2 and y goes from 0 to 4. Now, we're given this double integral to evaluate, and we know by Fubini's theorem we could set this up as an iterated integral, either integrating with respect to y first, then with respect to x, or with respect to x first, and then with respect to y. So just make sure when you're setting them up, you've got the proper bounds with the inside integral. dy, here are the bounds on y, and then x, here are the bounds on x. Similarly for this one. Now, which integral should we solve? Well, in this case, one of these integrals is going to be a lot easier than the other. Let's take a look. If we integrate with respect to y first, we have a product of functions here with respect to y. We're going to have to use integration by parts. Or we could integrate with respect to x first, and it's a basic integral. So this one is much easier. And we're going to evaluate this iterated integral, right? Because this, we said, needs integration by parts. And you know, there's always a student who wants to do it the hard way instead, but I'm going to suggest do it the easy way. You'll make less mistakes. You could certainly, for fun, check your answer by doing it the hard way as well, but on an exam, go for the easier way. So we'll evaluate this iterated integral. Now here, remember, we're integrating with respect to x. So that means this y is just a constant multiple, and it's going to carry to the integral. And now we have e to the x times y. Now we know that when we take the derivative, we get a factor of y that comes out. When we take an integral then, we're going to have to divide by y. So we're going to have 1 over y e to the xy. So simplifying, we're here. And now we want to plug in our x equals 2 and x equals 0 and subtract. Be careful here. I see a lot of students make mistakes when you're plugging in 0 for integration, because with polynomial functions it's always 0, but with exponentials it's not. So be careful and acknowledge that this e to the 0 is in fact 1. So here we have e to the 2y minus 1 getting integrated over y, and y going from 0 to 4. So we have a 1/2 e to the 2y minus y. We plug in our 4 and our 0, and we have 1/2 e to the 8th minus 4 minus 1/2. Again, recognize that the 2 times 0, e to the 0 is 1, so we do end up with 1/2 here. So we've got 1/2 e to the 8th minus 9/2. Or if you'd like to factor out your 1/2, you can write it like this. Either way is fine. Just one more thing I want to mention about double integrals are some properties of double integrals. And these are very similar to what we saw in Calc 1. And these properties result from the properties of sums. If we have the double integral over r of f plus g, that's the same as the double integral over r of f plus the double integral over r of g. If we have the double integral over r of a constant times a function, we can pull that constant out of the double integral. And if f is greater than or equal to g for all points in r, then the double integral over r of f is greater than or equal to the double integral over r of g. And with this, we'll conclude our lesson on double integrals over rectangles.